So here's something to think about as you're lying there tonight. Everything around you, the pillow under your head, the walls of the room, the air filling your lungs, all of it is made of atoms. You already know that, probably. It's one of those facts that gets repeated so often, it barely registers anymore. But here's the part that doesn't get repeated enough. The part that's genuinely wild if you stop and actually think about it. Those atoms, they don't behave like tiny little balls. They don't behave like anything you have ever encountered in your entire life. They follow rules so strange, so fundamentally different from the rules of the world you can see and touch, that when scientists first uncovered them, some of the most brilliant minds on the planet simply refused to accept what they were finding. Friendships ended. Careers were staked and sometimes lost. People who had dedicated their lives to understanding nature suddenly found themselves arguing about whether nature was even allowed to work the way the experiments said it did. That's what quantum physics is. It's the rule book for the very small, for atoms, for electrons, for particles of light. And it turns out that rule book is nothing like the one we use for baseballs and bridges and planets. And tonight, we're going to go through the whole thing, slowly, from the very beginning. We're going to meet the people who discovered these rules, and we're going to understand why the rules are what they are. And along the way, you're going to see how this strange science of the impossibly tiny ended up building the modern world. From the phone on your nightstand to the stars in the sky, there's no rush. If you fall asleep partway through, that's completely fine. That's sort of the point. The ideas will settle in either way. So let's start at the end of the 1800s, because that's when this whole story begins, and the mood in physics at the time is worth understanding. It was smug. That's the honest word for it. By the 1890s, most physicists felt like they had the universe pretty well figured out. Newton had explained motion and gravity 2 centuries earlier. James Clerk Maxwell had shown that electricity and magnetism were 2 faces of the same force, and that light itself was an electromagnetic wave. Thermodynamics was solid. The periodic table was filling in. There was this widespread sense, not universal, but common, that the fundamental laws of nature were all in place, and all that remained was to tighten up the details, to measure things to a few more decimal places. Lord Kelvin, one of the most prominent British physicists of the era, reportedly said something to the effect that physics was essentially complete, apart from 2 small clouds on the horizon, 2 little puzzles that hadn't been tidied up. And here's the thing, those 2 small clouds turned out to be hurricanes. One of them led to relativity. The other led to quantum mechanics. Between them, they demolished the entire classical worldview and replaced it with something so much stranger, so much richer, and so much more accurate that physics has never been the same. The cloud we care about tonight had to do with something utterly ordinary, the way hot things glow. You've seen this 1,000 times. A stovetop burner heating up from invisible warmth to a dull red, an iron poker in a fire turning orange, then yellow, then white. The sun, which is basically a ball of superheated gas, glowing a brilliant yellowish white. The color of a hot object tells you its temperature. This was well understood experimentally by the 1890s. Physicists had made careful measurements of exactly how much energy a hot object radiates at every different wavelength of light, and they had beautiful curves showing this relationship. The curves had a very particular shape. They rose up, peaked at some wavelength that depended on the temperature, and then fell off again at shorter wavelengths. And then they tried to explain those curves using the physics they had, and the prediction was a catastrophe. Literally. They called it the ultraviolet catastrophe. Here's why. Classical physics, Maxwell's equations combined with thermodynamics, predicted that a hot object should radiate more and more energy as you go to higher and higher frequencies. Toward the ultraviolet and beyond, The energy should just keep climbing, all the way to infinity. Every warm object in the universe should be blasting out infinite amounts of high-frequency radiation. Your coffee cup should be lethal. The math was clear, and it was clearly insane. The prediction bore no resemblance to reality. Something was deeply, fundamentally wrong. And this is where a meticulous, conservative, almost stubbornly methodical German physicist comes into the story. Max Planck. You need to understand Planck to appreciate what happened next, because the man and the moment were perfectly, almost comically, mismatched. Planck was not a revolutionary by temperament. He was born in 1858 in Kiel into a family of academics and theologians. He was orderly, proper, a creature of habit. He loved thermodynamics with a quiet passion. When he was young, one of his professors told him there was nothing new to discover in physics, that the field was essentially finished. Planck supposedly replied that he wasn't looking to discover anything new. He just wanted to understand the foundations more deeply. This is the man who was about to ignite the biggest revolution in the history of science. In the year 1900, Planck was wrestling with the black-body radiation problem. He was trying to find a mathematical formula that would match the experimental data, that beautifully measured curve showing how much energy a hot object radiates at each frequency. And he found one. After weeks of intense work, he managed to write down a formula that fit the data perfectly. Not roughly, not with some fudge factors. Perfectly. But here's where it gets strange. To make his formula work, Planck had to assume something that didn't make any sense in classical physics. He had to assume that energy couldn't be emitted or absorbed in just any arbitrary amount. Instead, it had to come in discrete chunks, specific, indivisible packets. He called them quanta, from the Latin for how much, and the size of each quantum was determined by the frequency of the radiation, multiplied by a new constant, a tiny, fundamental number that would eventually bear his name. Planck's constant, the letter H. Try to feel the weight of what Planck was saying, because it contradicts everything our everyday experience tells us. In our world, energy seems smooth. You can dim a light to any brightness you like. You can heat water to any temperature. Energy feels continuous, like water pouring from a tap. You can have any amount. What Planck was proposing is that energy is actually grainy. It's more like sand. Up close, it comes in tiny individual grains, and you can't have half a grain. You can have 1, 2, 10, a million, but always whole numbers, always discrete, and the number itself, Planck's constant, is fantastically small, about 6.626 times 10 to the negative 34 joule seconds. That's a 0, then a decimal point, then 33 more zeros, and then a 6. It's so tiny that in everyday life, the graininess is totally invisible. The quanta are so small that energy looks perfectly smooth, the same way a sandy beach looks smooth from an airplane. But at the atomic scale, where everything is small, those grains matter enormously. Now, here's the thing about Planck that makes this story so human. He didn't believe his own idea, not really. He thought the quantum hypothesis was a mathematical trick, a clever device that happened to give the right answer, not a real description of how nature works. He called it an act of desperation. He'd tried everything else and nothing worked, so he tried this strange assumption and it fit the data, and he presented it to the German Physical Society in October and December of 1900, and then he spent years trying to undo it. He wanted to find a way back to classical physics, to make the quantum go away. He never could. It was December 14th, 1900, the day he presented his derivation, and most historians of physics consider that the birthday of quantum theory. Planck lit a fuse that night. He didn't know it yet. Almost nobody did. but the fuse was burning. And the person who picked up that fuse and carried it forward was someone you've probably heard of, though maybe not in this context. Albert Einstein. In 1905, Einstein was 26 years old, working at the Swiss Federal Patent Office in Bern as a third-class technical examiner. He couldn't get an academic job. He evaluated other people's inventions during the day and did physics on the margins of his life, evenings, lunch breaks, weekends. And in that single year, working in near-total intellectual isolation, he published 4 papers that would each have been enough to make a career. One founded special relativity. Another proved that atoms actually exist by explaining the jittery motion of pollen grains in water, Brownian motion. But the one we care about tonight is the paper on the photoelectric effect, because it's the one that took Planck's reluctant idea and pushed it somewhere Planck never intended it to go. Here's the puzzle Einstein was looking at. When you shine light on certain metals, electrons pop off the surface. This is the photoelectric effect, and it had been known since Heinrich Hertz first observed it in 1887. Now, if light is a wave, as Maxwell had proved, you'd expect that making the light brighter, a bigger wave, would knock electrons off with more energy, more brightness, more punch. Makes sense, right? But the experiments showed something different. The energy of the ejected electrons depended on the color of the light, not the brightness. Shine dim blue light, and you get fast electrons. Shine blindingly bright red light, and you might get no electrons at all. Brightness only changed how many electrons popped off, not how fast each one flew. Classical wave theory couldn't explain this. It made no sense at all. Einstein's solution was elegant and bold. He said, what if light itself comes in quanta? Not just the emission and absorption, as Planck had cautiously suggested, but the light itself, traveling through space, exists as individual packets of energy. Each packet, which we'd later call a photon, carries an amount of energy equal to Planck's constant times the frequency of the light. High-frequency light, like blue or ultraviolet, carries more energy per photon. Low-frequency light, like red, carries less. When a photon hits an electron in the metal, it's a one-on-one collision. If the photon carries enough energy to tear the electron free, the electron escapes, and any leftover energy becomes its speed. If the photon doesn't carry enough energy, if it's a red photon and the job requires blue, then nothing happens. 1,000 gentle taps can't do what one firm knock accomplishes. This was far more radical than anything Planck had proposed. Planck had quantized the oscillators in matter. Einstein was quantizing light itself. He was saying that electromagnetic radiation, this thing Maxwell had shown was a continuous wave, also has a particle nature. It comes in lumps, and here's the beautiful, maddening result. Both descriptions are true. Light behaves like a wave when you send it through 2 slits and watch it create interference patterns. Light behaves like a particle when it knocks electrons out of metal. The same entity showing you 2 completely different faces depending on how you look at it. This is wave-particle duality, and it's the first deep strangeness of quantum physics. We're going to live with it all night, so let it settle in. The universe doesn't owe us a single, tidy picture. Even Planck himself thought Einstein had gone too far. When Planck wrote a recommendation for Einstein's membership in the Prussian Academy of Sciences in 1913, he praised Einstein's many achievements, but specifically noted that Einstein had sometimes overshot in his speculations, pointing to the light quantum hypothesis as an example. Planck was essentially saying, brilliant guy, but the photon thing is probably wrong. He was wrong about that. It was one of the most important ideas in the history of physics, and it's the paper that eventually won Einstein the Nobel Prize. Not relativity, as most people assume, but the photoelectric effect. But before the full implications of Einstein's photon idea could sink in, physics was about to face another crisis, this time from inside the atom itself. And the story of how that crisis unfolded involves a New Zealander with a booming voice and a talent for smashing things together to see what happened. His name was Ernest Rutherford, and the experiment he designed in 1909 would reveal something about the structure of matter that nobody expected and that classical physics couldn't survive. By the early 1900s, physicists knew atoms existed. They knew atoms contained electrons. J.J. Thomson had discovered the electron in 1897 at the Cavendish Laboratory in Cambridge by bending beams of cathode rays with electric and magnetic fields and measuring the charge-to-mass ratio of the particles. Thomson proposed a model of the atom that's sometimes called the plum pudding model, electrons embedded in a diffuse blob of positive charge, like raisins scattered through a pudding. It was a reasonable guess given what was known, and for a few years, it was the standard picture. Then Rutherford blew it apart. Working at the University of Manchester, Rutherford directed two of his researchers, Hans Geiger, a German physicist, and Ernest Marsden, an undergraduate student who was only about 20 years old, to fire alpha particles at a thin foil of gold. Alpha particles are helium nuclei, little positively charged bullets. The idea was that if Thomson's model was correct, if the positive charge in the atom was spread out like a fog, then the alpha particles should sail right through the foil with only minor deflections, like shooting bullets through mist. Most of them did exactly that, but some of them bounced back. A small fraction, maybe 1 in 8,000, came ricocheting back toward the source at large angles. Some came almost straight back. Rutherford later said, "It was the most incredible event of his life." He compared it to firing a 15-inch artillery shell at a piece of tissue paper and having it come back and hit you. Months of analysis followed. Thousands of scintillation flashes on a zinc sulfide screen, each one painstakingly recorded by Geiger and Marsden, working in darkened rooms, their eyes adapted to see the faintest glimmers. And when Rutherford worked through the mathematics, the conclusion was inescapable. Almost all the mass and all the positive charge of the atom had to be concentrated in a fantastically tiny region at the center, the nucleus. How tiny? If you scaled an atom up to the size of a cathedral, the nucleus would be a fly buzzing around inside. The atom was almost entirely empty space, the solid world around you, everything that feels firm and substantial. Your bed, the floor, the walls, is overwhelmingly nothing. But Rutherford's nuclear atom had a devastating problem. According to classical electromagnetism, it couldn't exist, not for more than a tiny fraction of a second. Here's why. If the electrons orbit the nucleus the way planets orbit the sun, they're constantly accelerating. Because circular motion is acceleration, your direction is always changing. And Maxwell's equations say, unambiguously, that any accelerating charged particle must radiate electromagnetic energy. So the orbiting electrons should be constantly bleeding energy, spiraling inward, and within about 100 millionth of a second, every electron should crash into the nucleus. Every atom in the universe should collapse into a flash of radiation almost instantly. Obviously, they don't. You're lying there, made of atoms, and they're perfectly stable. Something was profoundly wrong with the classical picture. And this is where a young Danish physicist named Niels Bohr enters the story. And honestly, Bohr is one of the most important and most fascinating figures in all of 20th century science. He was born in Copenhagen in 1885. His father was a professor of physiology. His mother came from a prominent banking family. The household was intensely intellectual. Debates about philosophy and science were dinner table routine. His younger brother Harold became a brilliant mathematician and, of all things, an Olympic silver medalist in football with the Danish national team. Niels himself was thoughtful, deliberate, sometimes agonizingly slow to formulate his ideas, but when he got there, the ideas were usually profound. He had a way of speaking that was so hedged and qualified that even other physicists sometimes couldn't tell what he was claiming. There's a story, possibly apocryphal but entirely in character, that after one of Bohr's lectures, a colleague said he understood every sentence individually, but had no idea what the lecture was about. In 1912, Bohr went to Manchester to work with Rutherford, and there he confronted the impossible instability of the nuclear atom head-on, and he did something audacious. He didn't try to fix classical physics. He didn't look for some clever loophole in Maxwell's equations. Instead, he essentially said, "The classical rules don't apply here." And then he wrote new ones. In 1913, Bohr published 3 landmark papers, his great trilogy, laying out what we now call the Bohr model of the atom. The key idea was this: electrons can only orbit the nucleus at certain specific, discrete distances, certain allowed orbits. And when they're in one of these orbits, they don't radiate energy. They just don't. It's a postulate, a rule, stated without classical justification. Bohr was declaring, in effect, that the universe has rules Maxwell never knew about. Which orbits are allowed? Here Planck's constant shows up again, that tiny number h that keeps threading through this whole story. Bohr said the allowed orbits are the ones where the electron's angular momentum is a whole number multiple of h divided by 2 pi. The angular momentum can be 1 times that value, or 2 times, or 3, but nothing in between. The electron can be in the first orbit, or the second, or the 10th, but never at 1.5 or 4.7. It's quantized, discrete, lumpy, and when an electron jumps from one orbit to another, it absorbs or emits a photon whose energy exactly equals the difference between the 2 orbits. Drop from a higher orbit to a lower one, emit a photon, absorb a photon of precisely the right energy, jump up. Because the orbits are discrete, the energy differences are discrete, which means the photons have very specific frequencies, very specific colors, and here's why that matters enormously. For decades, physicists had known that when you excite a gas, hydrogen for instance, and look at the light it emits through a prism, you don't see a smooth rainbow. You see sharp, bright lines at very specific wavelengths, with darkness in between. Each element has its own unique pattern of lines, like a fingerprint. A Swiss schoolteacher named Johann Balmer had found a mathematical formula in 1885 that predicted the visible spectral lines of hydrogen with stunning accuracy, but nobody knew why the formula worked. It was just a pattern, a numerical coincidence waiting for an explanation. Bohr provided the explanation. When he calculated the energies of his allowed orbits for hydrogen and then calculated the frequencies of photons emitted when electrons jumped between them, the numbers matched Balmer's formula almost perfectly. Not roughly. The agreement was extraordinary. Einstein, hearing about it, reportedly said something like, "Then this is one of the greatest discoveries." And he was right. Bohr's model, with its strange quantum rules, predicted the hydrogen spectrum with precision that nothing else could touch. If your theory predicts experimental results that no other theory can, the scientific world has to listen, no matter how strange the theory seems. But Bohr's model had limits. It worked beautifully for hydrogen, with its single electron. When physicists tried to extend it to helium, or heavier elements, it started to stumble. It was like a key that fits one lock perfectly, but jams in every other. Something deeper was needed, a more general framework, a new kind of mechanics for the quantum world. And in the mid-1920s, That framework arrived, born from an extraordinary burst of creativity by a generation of physicists, many of them barely out of their 20s, who would build the most successful theory in the history of science. The period from about 1923 to 1928 is sometimes called the golden age of quantum physics, and if you're a certain kind of nerd, the roster of characters reads like an all-star team. Werner Heisenberg, barely into his 20s. Erwin Schrödinger, an Austrian with a complicated personal life and an elegant mathematical mind. Paul Dirac, so quiet he once reportedly said nothing during an entire dinner party. Max Born, Wolfgang Pauli, Louis de Broglie, each of them contributing a crucial piece of the puzzle. But before any of them could build the full theory, one more wild idea had to fall into place. It came from a French aristocrat who asked a beautifully simple question. Louis de Broglie held the title of prince. The de Broglie family had been prominent in French politics and military affairs for generations. He'd originally studied history at the Sorbonne, but his older brother Maurice was a physicist working on X-rays, and something about those dinner table conversations about atoms and radiation pulled Louis towards science. By 1923, he was working on his doctoral thesis, and the question he kept turning over was this. Einstein had shown that light, which everyone treated as a wave, also behaves like a particle. So shouldn't the reverse be true? Shouldn't electrons, which everyone treats as particles, also behave like waves? Think about how bold that is. An electron has mass. It has charge. You can deflect it with a magnet. You can see its track in a cloud chamber. And de Broglie was saying, this thing also ripples. It also has a wavelength. And he didn't just wave his hands about it. He wrote down a formula. The wavelength of any particle equals Planck's constant divided by the particle's momentum. Lambda equals h over p. Notice what's sitting in that equation. Planck's constant again. That same tiny number that keeps showing up like a golden thread running through the entire tapestry. For anything you can hold in your hand, a tennis ball, a grain of sand, the mass is so huge compared to Planck's constant that the wavelength comes out absurdly small, trillions of times tinier than an atomic nucleus. You'd never detect it. That's why the everyday world doesn't seem wavy. But for an electron, which is incredibly light, the wavelength turns out to be roughly the size of an atom, and that changes everything. Here's why. Remember how Bohr's model had this mysterious rule that electrons could only occupy certain orbits, and nobody could explain why? De Broglie's idea explained it. If an electron is a wave circling the nucleus, that wave has to connect back up with itself after going all the way around. It has to form a standing wave, like a vibrating guitar string, which can only vibrate in certain patterns because the ends are fixed. If the electron wave doesn't fit neatly around the orbit, if you end up with 1.5 wavelengths or 2 3/4, it destructively interferes with itself and cancels out. That orbit simply can't exist. The only orbits that survive are the ones where a whole number of wavelengths fits around the circumference. And when you work out the math, those orbits are exactly the ones Bohr postulated. The quantization of electron orbits isn't some mystical decree. It's a natural consequence of electrons being waves. It's the same reason a flute can only play certain notes. De Broglie presented this in his doctoral thesis in 1924. His thesis committee wasn't sure what to make of it. One of them sent it to Einstein for a second opinion, and Einstein reportedly replied that de Broglie had lifted a corner of the Great Veil. The thesis was accepted, and 3 years later, the prediction was experimentally confirmed. Clinton Davison and Lester Germer at Bell Labs in New York fired electrons at a nickel crystal and saw a diffraction pattern, the electrons scattering off the crystal like waves through a grating. Independently, George Paget Thomson showed the same thing with thin metal films. And here's a delicious detail. George Thomson was the son of J.J. Thomson, the man who discovered the electron as a particle. Father proves it's a particle, son proves it's a wave. Both won Nobel Prizes, both were right. Welcome to quantum physics. So by the mid-1920s, the evidence is piling up. Energy is quantized. Light is both wave and particle. Matter is both wave and particle. Bohr's atom works for hydrogen, but breaks for everything else. The classical framework is in tatters. What's needed isn't another patch, another clever workaround. What's needed is a completely new mechanics, a replacement for Newton's laws at the atomic scale, and in 1925 and 1926, it arrived from two completely different directions, almost simultaneously. The first came from Werner Heisenberg, and the circumstances are wonderful. In the summer of 1925, Heisenberg was 23 years old, working as an assistant to Max Born in Göttingen. He was suffering terribly from hay fever. His face was swollen, he could barely see. So he asked for leave and took a ferry to Helgoland, a tiny rocky island in the North Sea, with almost no vegetation, and crucially, almost no pollen. And there, alone on that wind-swept rock, he worked through the nights on a radical new approach to quantum physics. Heisenberg's idea was to throw out everything you couldn't directly observe. You can't see an electron orbiting a nucleus. You can't watch it trace a path. What you can observe are the spectral lines, the frequencies and intensities of the light atoms emit and absorb. So Heisenberg decided to build a theory entirely out of observable quantities. He constructed arrays of numbers describing the relationships between energy states and transition probabilities. He didn't ask where the electron was. He only asked about what you could actually measure. The mathematics he ended up with was strange. When he multiplied his arrays together, the order mattered. A times B did not equal B times A. In ordinary arithmetic, 3 times 5 is the same as 5 times 3. But Heisenberg's quantities didn't obey that rule. This non-commutativity disturbed him deeply. He later recalled staying up all night checking his calculations, and when he confirmed the result at 3 in the morning, he was too wired to sleep and walked to the tip of the island to watch the sun rise over the sea. When he brought the work back to Göttingen, Max Born looked at it and immediately recognized the mathematical structure. Heisenberg had reinvented matrix algebra. The arrays were matrices, and the fact that matrix multiplication doesn't commute is a basic property of matrices that any mathematician would know. Born, together with his student Pascual Jordan, helped formalize the theory into what became matrix mechanics, the first complete, self-consistent version of quantum mechanics. It worked. It predicted spectral lines correctly, even for atoms more complex than hydrogen, but it was also abstract to the point of being almost impenetrable. Most physicists found it incredibly hard to work with. There was no picture, no visualization, just arrays of numbers and algebraic operations. It was like doing physics blindfolded. And then, just months later, Erwin Schrödinger published a completely different approach. Schrödinger was older than most of the other quantum revolutionaries. He was in his late 30s, and he was inspired by de Broglie's matter waves. If electrons are waves, Schrödinger reasoned, there should be a wave equation governing them, just as Maxwell's equations govern light waves. So he set out to find it. The circumstances of the discovery have become the stuff of legend. In December 1925, Schrödinger went on holiday to a villa in Arosa, in the Swiss Alps, with a woman who was not his wife. History has never established who she was. And during that retreat, in a burst of intense creativity, he derived the equation that now carries his name, the Schrödinger equation. It describes how a mathematical object called the wave function evolves over time. Now, physicists loved Schrödinger's approach because it looked familiar. It was a differential equation, the kind of mathematics they'd been using for centuries. You could visualize things. You could picture the wave function sloshing around. Schrödinger himself believed the wave function was a real, physical wave, that the electron was literally smeared out in space. And here was the beautiful part. Schrödinger's wave mechanics and Heisenberg's matrix mechanics, despite looking completely different, gave exactly the same answers for every problem. Schrödinger himself proved they were mathematically equivalent, two different languages describing the same physics, the way you can describe a circle using Cartesian coordinates or polar coordinates. But then came the question that would consume physics for years, a question that honestly still hasn't been settled. What does the wave function actually mean? What is it telling us about reality? The answer, or at least the answer that most physicists eventually accepted, came from Max Born in 1926, and it was both revolutionary and deeply unsettling. Born pointed out a problem with Schrödinger's picture. When you solve the wave equation for an electron in an atom, the wave function spreads out over a region of space. It doesn't sit at one point. But when you actually detect the electron, when you measure it, you always find it at a specific location. You never see half an electron here and half there. So the wave function can't literally be the electron smeared out. Instead, Born proposed something subtler. He said the wave function gives you probabilities. The square of the wave function at any point in space tells you the probability of finding the electron at that point if you make a measurement. Before you measure, the electron doesn't have a definite position. There's just a cloud of possibilities, described by the wave function. After you measure, you get a specific result, and the wave function collapses to a spike at that point. Let that sink in. For the first time in the history of physics, a fundamental theory was saying that nature is inherently probabilistic, not because we lack information, not because our instruments are imprecise, but fundamentally, irreducibly random. The universe, at its deepest level, deals in probabilities, not certainties. And if Born's probabilistic interpretation wasn't strange enough, Heisenberg was about to deliver another blow to our intuitions about what we can know. In 1927, he formulated the uncertainty principle, one of the most famous ideas in all of science, and one of the most widely misunderstood. Here's what it actually says. There are pairs of physical properties, position and momentum, energy and time, that cannot both be known with perfect precision simultaneously. The more precisely you pin down one, the less precisely you can know the other. And this isn't a limitation of our instruments. It's a feature of reality itself. The easiest way to think about it is this. To measure the position of an electron, you need to bounce something off it, say, a photon of light. To get a precise position, you need a short wavelength photon, because short wavelengths give finer resolution. But short wavelength photons carry more energy, and when they hit the electron, they kick it hard, changing its momentum unpredictably. Use a gentle, long wavelength photon to preserve the momentum, and now your position measurement is blurry. You can't win. The act of measuring one quantity inevitably disturbs the other. Nature has a built-in limit to what can be simultaneously known. The mathematical statement is precise. The uncertainty in position, multiplied by the uncertainty in momentum, can never be less than Planck's constant divided by 4 pi. And there it is again, Planck's constant, setting the scale for quantum strangeness. Because Planck's constant is so tiny, the uncertainty principle is invisible in everyday life. You can know both the position and velocity of a baseball as precisely as you'd ever want. But at the atomic scale, the principle is dominant. An electron confined to a small space has an inherently large uncertainty in its momentum, which means It's jittering around unpredictably. You simply cannot know everything about a quantum particle at once. The universe doesn't allow it. Together, Born's probability interpretation and Heisenberg's uncertainty principle form the backbone of what's called the Copenhagen interpretation of quantum mechanics, the framework championed by Bohr and Heisenberg at Bohr's Institute in Copenhagen. The Copenhagen view says the wave function is the most complete description of a quantum system that's possible. Before measurement, particles don't have definite properties. The act of measurement doesn't reveal a pre-existing reality. It creates the reality. And if that makes you uncomfortable, you're in spectacular company. Because the person who objected most loudly and most persistently was someone who had done more than anyone else to start the quantum revolution in the first place. Albert Einstein had deep, principled objections to the idea that God plays dice with the universe, and the debate between Einstein and Bohr would become one of the greatest intellectual confrontations in the history of human thought. But before we get there, there's another piece of the quantum puzzle that needs to fall into place, a piece that's so beautiful, so mathematically perfect, that it feels almost like the universe was showing off, and it came from a man so quiet that words seemed to physically pain him. Paul Dirac was born in Bristol, England, in 1902. His father was a Swiss-born French teacher, reportedly so strict that the household was run more like a barracks than a home. Dirac later said that as a child, he learned it was better to say nothing than to say something incorrect, because his father would punish him for grammatical mistakes. Whether that story is literally true or slightly embellished, the result was a man of almost supernatural reticence. At conferences, Dirac would sit silently for hours. When he did speak, his words were precise, spare, and devastatingly to the point. There's a famous story, probably true, Dirac's stories usually are, that after a lecture, a member of the audience said, "I don't understand your equation on the top right of the blackboard." A long silence followed. The moderator eventually prompted Dirac to respond. Dirac said, "That was a statement, not a question." But behind that silence was one of the most extraordinary mathematical minds in the history of physics. In 1928, when he was just 25 years old, Dirac did something remarkable. He combined quantum mechanics with Einstein's special relativity, something nobody had been able to do properly, and derived a single equation describing the electron, the Dirac equation. And it was beautiful, not just aesthetically, though it was that, but because it automatically, without being asked, explained things that had been put into the theory by hand before. Here's what I mean. When physicists had been trying to understand the electron, they'd noticed that it had a property called spin, an intrinsic angular momentum, as if the electron were spinning on its axis. But this spin had been added to quantum mechanics, somewhat awkwardly, as an extra ingredient bolted on from the outside. Dirac's equation produced spin naturally. It fell right out of the mathematics, as a necessary consequence of combining quantum theory with relativity. The equation also predicted the exact magnetic properties of the electron, matching experimental measurements with extraordinary precision. It was as if the universe had been trying to tell physicists about spin all along, and Dirac was the first to listen in the right mathematical language. But the Dirac equation did something else, something nobody expected, something that went beyond explaining what was already known and ventured into genuine prediction. The equation had two sets of solutions. One set described ordinary electrons with positive energy. The other set described something with negative energy. Now, negative energy solutions are a problem. In principle, ordinary electrons could drop into these negative energy states, releasing radiation and cascading down forever. The universe would be unstable. Dirac needed a way to prevent this. His solution was ingenious and bizarre. He proposed that all the negative energy states are already filled. Every single one. A vast, invisible sea of negative energy electrons filling all of space, what became known as the Dirac Sea. You'd never notice this sea, because it's everywhere, always, like a perfectly uniform background. But here's the crucial part. If you pumped enough energy into one of these negative energy electrons, say, with a high-energy photon, you could kick it out of the sea and up into a positive energy state. That would create an ordinary electron where there hadn't been one before, and it would also leave behind a hole in the sea, an absence. And that hole, Dirac realized, would behave like a particle with the same mass as an electron, but with the opposite charge, a positive electron. At first, Dirac was cautious about this prediction. He initially hoped the holes might be protons, but the math didn't work. Protons are nearly 2,000 times heavier than electrons. Eventually, he had to accept that his equation was predicting the existence of an entirely new type of particle, a mirror image of the electron, same mass, opposite charge, antimatter. Think about what that means. A mathematical equation, derived from pure theoretical reasoning, combining two existing theories and demanding consistency, predicted the existence of a particle that nobody had ever seen and nobody had any reason to expect. That's the kind of prediction that makes you believe mathematics is the language of the universe, not just a tool we invented for bookkeeping. And then, in 1932, an American physicist named Carl Anderson found it. Working at Caltech, Anderson was studying cosmic rays, high-energy particles that rain down on Earth from space. He built a cloud chamber, a device where charged particles leave visible trails of condensation as they fly through supersaturated vapor, and he placed it in a strong magnetic field so that positive and negative charges would curve in opposite directions. And in his photographs, he kept seeing tracks that curved the wrong way. They looked like electron tracks, same mass, same ionization, but they curved in the direction a positively charged particle would curve. Anderson called them positrons, antimatter, exactly what Dirac's equation had predicted 4 years earlier. This was a watershed moment. It was the first time a fundamental particle had been predicted theoretically before being discovered experimentally. The positron wasn't just a surprise finding in a lab. It was a confirmation that the mathematical structure of quantum mechanics, when taken seriously, could reveal features of reality that nobody had imagined. Nature was even richer, even more layered than anyone had dared to think. And the implications went further. If the electron has an antiparticle, then so does every other particle. Antiprotons were discovered in 1955 at the Berkeley Bevatron, and antineutrons followed a year later. We now know that for every type of matter particle, there's a corresponding antimatter particle with the same mass and opposite quantum numbers. When a particle meets its antiparticle, they annihilate each other, converting their combined mass entirely into energy, according to Einstein's E equals mc squared. Pure energy from the destruction of matter. It's not science fiction. It happens all the time. PET scanners in hospitals use positron annihilation to image your body. But let's come back to the main thread, because while Dirac was unifying quantum mechanics with relativity and predicting antimatter, the philosophical battle over the meaning of quantum mechanics was reaching its peak, and it centered on two of the towering figures of 20th century physics, Einstein and Bohr. The debates between them played out most famously at a series of Solvay conferences in Brussels, invitation-only gatherings of the world's leading physicists, funded by the Belgian industrialist Ernest Solvay. The fifth Solvay conference, in 1927, is the most legendary. There's a famous photograph of the attendees, 29 physicists arranged in 3 rows, and among them, are Einstein, Bohr, Heisenberg, Schrödinger, Dirac, Born, Pauli, de Broglie, Marie Curie, and about a dozen others. 17 of the 29 would become Nobel laureates. It might be the highest concentration of human genius ever assembled in one place. At that conference, Einstein began his campaign against the Copenhagen interpretation. His strategy was clever. He didn't attack the math. He knew the math worked. Instead, he constructed thought experiments designed to show that quantum mechanics must be incomplete. He wanted to prove that it was possible, at least in principle, to know more about a quantum system than the uncertainty principle allowed. Each morning at breakfast, Einstein would present Bohr with a new scenario, some cleverly designed arrangement of slits and mirrors and clocks intended to demonstrate that you could simultaneously know both the position and momentum of a particle. And Bohr would spend the entire day agonizing over it, pacing, sketching diagrams, talking to himself. And by dinner, Bohr would find the flaw, every single time. One particularly dramatic exchange came at the 1930 Solvay conference. Einstein proposed a box filled with radiation, with a clock-controlled shutter that opens for a precisely known interval, letting out a single photon. You weigh the box before and after to determine the photon's energy from the tiny mass change via E equals mc squared. Since you know when the shutter opened and how much energy left, you'd know both time and energy precisely, violating the uncertainty principle. Bohr was reportedly deeply shaken that evening, but by morning he'd found the answer, and the irony was exquisite. He used Einstein's own general relativity to do it. The act of weighing the box requires it to move in a gravitational field, and general relativity says a clock moving in a gravitational field experiences time dilation. That movement introduces just enough uncertainty in the timing to preserve Heisenberg's principle. Einstein was defeated by his own theory. That must have stung. But Einstein never gave up. He just changed his angle of attack. By the mid-1930s, he stopped trying to show quantum mechanics was self-contradictory, and instead tried to show it was incomplete, that it was missing something real. And in 1935, he produced his most famous and most lasting argument. Working with Boris Podolsky and Nathan Rosen, Einstein published a paper known universally by their initials, EPR. The question in the title was blunt: can quantum mechanical description of physical reality be considered complete? Their answer was no. The EPR argument goes like this, in simplified form. Imagine a source that produces two particles flying off in opposite directions. These particles are created in a correlated state, what quantum mechanics calls entanglement, a term Schrödinger coined that same year. If you measure the spin of particle A and find it pointing up, quantum mechanics says particle B must be pointing down. The correlation is perfect. Now, according to Copenhagen, neither particle has a definite spin until you measure it. The spin is genuinely undetermined, but the instant you measure particle A, finding its spin up, you immediately know particle B is spin down, even if particle B is on the other side of the galaxy. How does particle B know what happened to particle A? If the information travels instantaneously, it violates relativity. Einstein called it spooky action at a distance, and he meant it dismissively. His proposed alternative was simpler and more intuitive. Both particles had definite spins all along, from the moment of creation. Quantum mechanics just couldn't capture that information. The theory was incomplete. There were hidden variables, real, definite properties that particles carry, but that quantum mechanics is blind to. It was like a pair of gloves in two boxes. Open one box and find the left glove, and you instantly know the other box has the right glove. No spooky action needed. The gloves were always left and right. This argument lingered for nearly 3 decades. Most physicists shrugged and went back to work. Quantum mechanics gave the right answers for practical calculations, regardless of what you believed about what was really going on underneath. The interpretation debate seemed like philosophy, not physics. But in 1964, a quiet Irish physicist named John Bell, working at CERN in Geneva, showed that the debate was not philosophical at all. It was experimental. Bell derived a mathematical inequality, Bell's inequality, that any theory with local hidden variables must obey. Think of it like a speed limit. If reality works the way Einstein hoped, certain statistical correlations between measurements on entangled particles can never exceed a particular value. But quantum mechanics predicts that in certain setups, they will exceed it. The correlations will be stronger than any local hidden variable theory can produce. This was no longer armchair philosophy. It was a concrete, testable prediction. And starting in the 1970s and accelerating in the 1980s, physicists went into their labs and tested it. The most famous early experiments were by Alain Aspect at the University of Paris-Sud in Orsay, France, in 1981 and 1982. Aspect created pairs of entangled photons, measured their polarizations at different angles, and tallied up the correlations. Crucially, he included rapid switching of the measurement settings while the photons were in flight, so that no signal, even one traveling at the speed of light, could carry information between the two detectors. The result was unambiguous. Bell's inequality was violated. Quantum mechanics won. The correlations were exactly what the theory predicted, and stronger than any local hidden variable theory could produce. Einstein's hope that particles carry definite properties all along was experimentally ruled out, at least in combination with locality, the principle that distant events can't instantaneously influence each other. The experiments have only improved since. In 2015, a team at Delft University in the Netherlands performed the first truly loophole-free Bell test, closing all known experimental gaps simultaneously. Same result. Quantum mechanics wins. Nature really is as strange as the theory says. Einstein died in 1955, 9 years before Bell published his theorem and decades before the experiments. He never knew the outcome. There's something poignant in that. The man who ignited the quantum revolution, spending his last decades fighting against where it led, and the universe, ultimately, siding with Bohr. But Einstein's questions weren't wasted. The phenomenon he tried to dismiss, entanglement, spooky action at a distance, turned out to be one of the most powerful resources in physics. It's the foundation of quantum computing, quantum cryptography, quantum teleportation. The very thing Einstein thought was absurd became the key to technologies he couldn't have imagined. And that brings us to a question we should dig into, because the story of quantum physics doesn't end with foundations. It kept growing, kept expanding, kept finding new layers of reality to describe, and one of the most ambitious extensions took the quantum framework and applied it not just to individual particles, but to the fields that permeate all of space. That extension, quantum field theory, would eventually produce the most precise and comprehensive theory of nature ever constructed, and the story of how it came together involves one of the most charismatic, unconventional, and brilliantly intuitive physicists who ever lived. His name was Richard Feynman, and he played the bongo drums, cracked safes for fun, and reinvented the mathematics of quantum physics. And it's worth pausing here to talk about one more thought experiment from this era, because it's become the most famous image in all of quantum physics, and it captures the strangeness of the measurement problem in a way that's never been topped. In 1935, the same year as the EPR paper, Erwin Schrödinger, the man who wrote down the wave equation, proposed a scenario that he intended as a reductio ad absurdum, a way of showing how ridiculous the Copenhagen interpretation becomes when you push it to its logical conclusion. He described a cat. Here's the setup. Put a cat in a sealed box. Inside the box, there's a tiny amount of radioactive material, a Geiger counter, a vial of poison, and a mechanism connecting them. If a single atom decays, the Geiger counter detects it, the mechanism breaks the vial, and the cat dies. If no atom decays, the cat is fine. Now, according to quantum mechanics, before you observe it, the radioactive atom is in a superposition. It has both decayed and not decayed, simultaneously. And since the cat's fate is tied to the atom's state, the cat itself is, according to the strict application of quantum mechanics, in a superposition of alive and dead. Not alive or dead. Not alive with some probability and dead with some probability. Both, simultaneously. Until you open the box and look. Schrödinger meant this as a critique. He was saying, look how absurd this gets when you scale it up from atoms to cats. Surely a cat can't be both alive and dead. There must be a point at which quantum superpositions resolve into definite classical outcomes, and the Copenhagen interpretation doesn't tell us where that point is. And he was right. This is the measurement problem, and it remains one of the deepest unresolved questions in physics today. What constitutes a measurement? When does the wave function collapse? Does it collapse at all? Or do the different outcomes simply exist in parallel branches of reality, as the many worlds interpretation suggests? These questions have haunted physics for nearly a century. Schrödinger's cat was supposed to kill the Copenhagen interpretation. Instead, it became the interpretation's most famous mascot. Life is funny that way. Electrodynamics in a way that nobody else could have dreamed up. Feynman was born in 1918 in Far Rockaway, Queens, New York. His father was a uniform salesman who never went to college but had a deep love of science and spent hours teaching young Richard to think about the world with curiosity and skepticism. Feynman was a natural tinkerer. He fixed radios as a teenager, built an alarm system for his bedroom, and once rigged a device to automatically open the door of a laundry cart so he wouldn't have to get up from bed. By the time he got to MIT as an undergraduate and then Princeton for graduate school, it was clear he was something special. He wasn't just smart, he was creative in a way that bordered on strange. He approached problems from directions nobody else would consider, using intuitions that seemed to come from somewhere outside the standard toolkit of physics. During World War II, Feynman worked on the Manhattan Project at Los Alamos, computing the physics of the implosion-type atomic bomb. But after the war, he turned his attention to a problem that had been tormenting quantum physicists for years. A problem with quantum electrodynamics, or QED. QED is the quantum theory of electromagnetism. It describes how electrically charged particles, like electrons, interact with each other by exchanging photons. It should be the most natural application of quantum mechanics to a force. After all, electromagnetism was the first force described by quantum theory. But there was a terrible problem. When you tried to calculate anything beyond the simplest interactions, the math blew up. You'd get infinities, not big numbers, literally infinite answers. The predicted mass of the electron was infinite. The predicted charge was infinite. The answers were nonsense. This was the infinity problem, and it paralyzed the field for nearly 2 decades. Physicists knew quantum electrodynamics should work, in principle, but the actual calculations produced garbage. It was like having a recipe that you know should make a cake, but every time you try to follow it, the oven catches fire. The solution came in the late 1940s, developed independently by 3 physicists: Feynman, Julian Schwinger, and Shinichiro Tominaga. Each developed their own version of a technique called renormalization, a systematic way of absorbing the infinities into the definitions of physical constants. The basic idea is subtle but profound. The infinities arise because virtual particles, fleeting quantum fluctuations that pop into and out of existence everywhere in space, affect the properties of real particles. An electron, for example, is constantly emitting and reabsorbing virtual photons, which in turn create virtual electron-positron pairs, and so on. This cloud of virtual activity modifies the electron's effective mass and charge. The raw, bare values that go into the equations are infinite, but the physical, measurable values, the ones you actually observe in experiments, are finite. Renormalization is the procedure for consistently separating the infinite bare values from the finite physical ones. Now, if that sounds like sweeping infinities under the rug, you're not alone. Plenty of physicists felt the same way. Dirac, who had created the theory that QED was trying to complete, was never happy with renormalization. He called the technique ugly and spent years looking for a more fundamental approach. But the thing about renormalization is this: it works. Spectacularly. Embarrassingly well. QED, once renormalized, makes predictions that agree with experiment to more decimal places than any other theory in the history of science. Here's the most famous example. The electron has a magnetic property, characterized by a number called its G factor. Classical physics predicts it should be exactly 2. Dirac's equation gives exactly 2, but experiments show it's very slightly more than 2. The deviation, the anomalous magnetic moment, comes from those swarms of virtual particles constantly buzzing around the electron. QED can calculate this deviation, and the calculation has been pushed to extraordinary precision. The theoretical prediction, including contributions from hundreds of thousands of Feynman diagrams, agrees with the experimental measurement to about 1 part in 10 trillion. That's like predicting the distance from Los Angeles to New York and being accurate to the thickness of a human hair. It's the most accurate prediction in the history of science. And speaking of Feynman diagrams, those deserve a moment because they're one of Feynman's most brilliant contributions, and they changed how physicists think about the quantum world. Before Feynman, calculating quantum electrodynamic processes meant wading through pages and pages of dense algebra. Feynman introduced a visual shorthand, little drawings showing particles as lines, photon exchanges as wiggly lines, and interactions as points where lines meet. Each diagram corresponds to a specific mathematical expression, and by drawing all the possible diagrams for a given process, you get all the contributions to the calculation. It sounds simple, almost childlike. And in a way, that was the genius of it. Feynman turned impenetrable algebra into pictures that even a student could start to grasp. Schwinger, who had developed an equally valid but far more formal approach, reportedly said that Feynman diagrams had brought computation to the masses. There was a slight edge to that comment. Schwinger was a precise, elegant mathematician who preferred rigorous derivation to intuitive pictures. But the impact was real. Feynman diagrams became the universal language of particle physics. Walk into any theoretical physics department in the world, and you'll find blackboards covered with them. In 1965, Feynman, Schwinger, and Tomonaga shared the Nobel Prize in Physics for their work on quantum electrodynamics. And QED became the template for something much larger. Because if you could build a quantum theory of the electromagnetic force, why not do the same for the other fundamental forces of nature? And this is where the story opens up into something vast. Because by the middle of the 20th century, physicists had discovered that the universe has not just one fundamental force, but 4. Gravity, which holds you to the Earth and keeps planets in orbit. Electromagnetism, which governs light and chemistry and everything electrical. the strong nuclear force, which binds protons and neutrons together inside atomic nuclei, and the weak nuclear force, which is responsible for certain kinds of radioactive decay. Gravity operates on the largest scales and is by far the weakest. Electromagnetism is much stronger and has infinite range. The strong force is the most powerful of all, but it only works at incredibly short distances within the atomic nucleus. And the weak force is even shorter ranged than the strong force, responsible for processes like beta decay, where a neutron transforms into a proton by emitting an electron and a ghostly particle called a neutrino. Wait, a neutrino? That's worth a brief detour. The neutrino was originally proposed in 1930 by Wolfgang Pauli, and the way he proposed it tells you a lot about both the man and the era. Physicists had been studying beta decay, the process where a radioactive nucleus emits an electron, and they'd found a disturbing problem. The emitted electrons didn't all come out with the same energy. They came out with a range of energies, from very low to some maximum. But if the nucleus was simply spitting out an electron, conservation of energy and conservation of momentum dictated that the electron should always have the same energy. The books didn't balance. Either conservation of energy was being violated at the subatomic level, or there was a missing particle, something invisible, carrying away the rest of the energy. Pauli chose option 2. In a famous letter addressed to a physics conference in Tübingen, a letter he began with, "Dear radioactive ladies and gentlemen," he proposed the existence of an extremely light, electrically neutral particle that was being emitted alongside the electron, but escaping undetected. He called it the neutron at first, though that name was soon reassigned to the neutral particle inside the nucleus, and Enrico Fermi renamed Pauli's particle the neutrino, Italian for little neutral one. The neutrino seemed almost imaginary for years. It has no electric charge. It barely interacts with anything. A neutrino can pass through a light year of solid lead and come out the other side without hitting a single atom. Pauli himself reportedly said he had committed a terrible sin. He had postulated a particle that could never be detected. But he was wrong about that. In 1956, Frederick Raynes and Clyde Cowan detected neutrinos using a nuclear reactor as a source and a carefully designed detector in South Carolina. Pauli, upon receiving the news by telegram, is said to have replied, "Everything comes to him who knows how to wait." But let's come back to the forces, because the second half of the 20th century saw one of the most ambitious intellectual projects in the history of science, the attempt to bring all the fundamental forces under the umbrella of quantum field theory, the way QED had brought electromagnetism. And the results of that project, the standard model of particle physics, represent the most comprehensive, most precisely tested description of nature that humans have ever achieved. The story begins with a zoo. By the 1950s and 1960s, particle accelerators, machines that smash particles together at enormous energies to see what comes out, were discovering new particles at an alarming rate. Pions, kaons, lambda particles, sigma particles, xi particles, omega particles. There were so many that physicists started calling it the particle zoo. It was exciting, but also deeply confusing. Were all these particles fundamental? Was each one its own basic building block? Enrico Fermi, overwhelmed by the proliferation, reportedly said, "If I could remember the names of all these particles, I would have been a botanist." The person who brought order to the chaos was Murray Gell-Mann, a physicist at Caltech who was brilliant, competitive, and knew it. Gell-Mann was a prodigy. He entered Yale at 15 and got his PhD from MIT at 21. He had an almost compulsive need to be right about everything, including the pronunciation of foreign words and the taxonomy of birds. but his physics was extraordinary. In 1961, he proposed a classification scheme called the Eightfold Way, which organized the known particles into geometric patterns based on their properties. It was like Mendeleev's periodic table, but for subatomic particles. And just like Mendeleev's table had gaps that predicted the existence of undiscovered elements, Gell-Mann's scheme had a gap that predicted a particle nobody had ever seen, the omega-minus baryon, with specific mass and properties. When it was discovered at Brookhaven National Laboratory in 1964, the physics world paid attention. But Gell-Mann went further. He asked, why do the patterns look the way they do? What's underneath? And in 1964, he proposed that protons and neutrons and all those other heavy particles, the hadrons, aren't fundamental at all. They're made of smaller, more basic particles. He called them quarks, a word he took from a line in James Joyce's Finnegan's Wake, 3 quarks for muster mark. Independently, George Zweig, a younger physicist at CERN, proposed essentially the same idea, calling them ACEs. But Gell-Mann had the better name, and the name stuck. The original quark model proposed 3 types, or flavors, of quarks: up, down, and strange. A proton, in this picture, is made of 2 up quarks and 1 down quark. A neutron is 2 down quarks and 1 up. The various exotic particles of the particle zoo were explained as different combinations of quarks. The math was elegant and the predictions were accurate, but there was a problem. Nobody could find a free quark. No matter how hard they smashed protons apart, quarks never appeared on their own. They always stayed locked inside their parent particles. This was baffling until physicists realized it was a feature, not a bug. The force that holds quarks together, the strong nuclear force, has a bizarre property unlike anything in everyday experience. While the electromagnetic force gets weaker as you pull 2 charged particles apart, the strong force gets stronger. Imagine 2 quarks connected by a kind of rubber band that gets tighter the further you stretch it. At close range, inside a proton, quarks move around almost freely. But try to pull one out, and the force resists with increasing intensity. Eventually, the energy you're pumping in to separate them is enough to create a new quark-antiquark pair, and you end up with new particles rather than free quarks. The quarks are permanently confined. You can never isolate one. The quantum theory that describes the strong force is called quantum chromodynamics, or QCD. It works on the same principles as QED, but with a crucial difference. Instead of electric charge, quarks carry a property called color charge: red, green, or blue, though these are just whimsical names, nothing to do with actual colors. And the force carriers, analogous to photons in electromagnetism, are called gluons. There are 8 types of gluons, and here's the kicker. Unlike photons, which carry no electric charge, gluons themselves carry color charge. They interact with each other. A photon can't interact with another photon directly, but gluons can and do. This self-interaction is what makes the strong force so complicated, so rich, and so different from electromagnetism. Meanwhile, the weak nuclear force was getting its own quantum field theory treatment. In the 1960s and 1970s, Sheldon Glashow, Abdus Salam, and Steven Weinberg showed that the weak force and electromagnetism could be unified into a single framework called the electroweak theory. At very high energies, the 2 forces are aspects of the same underlying interaction. At low energies, the energies of everyday life, they look completely different because the force carriers of the weak force are extremely massive, which limits the force's range to subatomic distances. These carriers, the W and Z bosons, were predicted by the theory and discovered at CERN in 1983 by a team led by Carlo Rubbia and Simon van der Meer, earning them the Nobel Prize the following year. So by the 1970s and 1980s, a picture was emerging. 3 of the 4 fundamental forces, electromagnetism, the strong force, and the weak force, had been described by quantum field theories. Gravity remained the stubborn holdout, resisting all attempts at quantum treatment. But the 3 quantum theories, taken together with the list of known fundamental particles, 6 quarks, 6 leptons including the electron and neutrinos, and the force-carrying bosons, formed a unified framework that became known as the Standard Model of particle physics. And here's what's remarkable about it. The Standard Model is not a tidy, beautiful theory in the way Einstein's general relativity is. It has a lot of moving parts. There are about 25 free parameters, numbers like particle masses and force strengths, that the theory doesn't predict, but instead takes from experiment. It doesn't include gravity. It doesn't explain dark matter or dark energy. Aesthetically, it's a bit of a patchwork, but experimentally, it's been validated to extraordinary precision. Every prediction it has made has been confirmed. Every particle it calls for has been found, including, finally, the most elusive one, the Higgs boson. The Higgs mechanism, proposed in 1964 by several groups of physicists including Peter Higgs in Edinburgh and François Englert and Robert Brout in Brussels, addressed a fundamental problem. Why do some force-carrying particles have mass, while others don't? Photons are massless. They travel at the speed of light. But the W and Z bosons are heavy, about 80 and 90 times the mass of a proton, respectively. And in the basic mathematics of quantum field theory, the force carriers come out massless. Something had to be giving them mass. The answer was a new field pervading all of space, the Higgs field. And the mechanism is actually quite intuitive, once you have the right picture. Imagine a celebrity walking through a crowded room. If the person is unknown, they pass through easily. No mass, no resistance. But if they're famous, people cluster around them, slowing them down, making it harder to change speed or direction. The Higgs field does something analogous to certain particles. Particles that interact strongly with the Higgs field acquire large masses. Particles that don't interact with it remain massless. The photon doesn't interact with the Higgs field, so it's massless. The W and Z bosons interact strongly, so they're heavy. The Higgs field also explains why quarks and electrons have mass, though the details are more nuanced. And associated with this field is a particle, the quantum excitation of the field, just as a photon is a quantum of the electromagnetic field. That particle is the Higgs boson, and finding it became one of the great quests of experimental physics. It took nearly 50 years. The problem is that the Higgs boson is heavy and short-lived. It requires enormous energies to produce and decays almost instantly into other particles. The machine that finally found it was the Large Hadron Collider, or LHC, at CERN, a circular accelerator 27 kilometers in circumference, buried underground beneath the French-Swiss border. The LHC accelerates protons to 99.9999991% of the speed of light and smashes them head-on, creating fireballs of energy from which new particles materialize. It's the biggest, most complex scientific instrument ever built. On July 4, 2012, physicists at CERN announced the discovery of a new particle with a mass of about 125 giga-electron volts, consistent in every measured property with the predicted Higgs boson. The auditorium was packed. Peter Higgs, then 83 years old, was in the room. When the results were announced, he reportedly wiped tears from his eyes. The next year, Higgs and Englert shared the Nobel Prize. The discovery of the Higgs completed the Standard Model. Every particle the theory predicted has now been found. It's a remarkable achievement, a single, consistent framework describing 3 of the 4 fundamental forces and all known matter particles, tested to phenomenal precision. And all of it is built on the foundations we've been talking about tonight. Quantized energy, wave-particle duality, probability amplitudes, the Pauli exclusion principle, Dirac's equation, the renormalization of quantum field theories. From Planck's reluctant quanta in 1900 to the Higgs boson in 2012, it's one continuous thread. But the Standard Model, for all its successes, is not the final word. We know it's incomplete. It doesn't include gravity. It doesn't explain why the universe is made of matter rather than antimatter. The laws of physics are almost perfectly symmetric between the two. Yet somehow, the universe managed to end up with a surplus of matter. It doesn't account for dark matter, which makes up about 27% of the universe's mass energy content, or dark energy, which makes up about 68% and is driving the accelerating expansion of the universe. The Standard Model describes the roughly 5% of the universe made of ordinary matter, the stuff we can see and touch. The rest is a mystery, and the deepest mystery of all may be gravity. General relativity describes gravity as the curvature of space-time, and it works beautifully at large scales. Planets, stars, galaxies. Quantum mechanics describes the behavior of particles at tiny scales, and it works beautifully there. But when you try to combine them, when you try to build a quantum theory of gravity, the mathematics breaks down in ways that make the infinities of old QED look tame. The problem is that space-time itself, the stage on which quantum physics plays out, becomes a dynamic, fluctuating quantum entity. Space at the smallest scales, the Planck scale, about 10 to the minus 35 meters, should be a roiling foam of quantum fluctuations, with the very geometry of space and time bubbling and morphing unpredictably. How to make sense of this is one of the great unsolved problems in physics, and approaches like string theory and loop quantum gravity have been pursuing it for decades without a definitive answer. But let's leave the frontiers for a moment and come back to the quantum world we already understand, because there's something we haven't really talked about yet, and it's one of the most important quantum phenomena in all of engineering and nature. It's called quantum tunneling, and once you understand it, you'll see it everywhere, from the nuclear furnace in the heart of the sun to the flash memory chip in your phone. Quantum tunneling is this. A particle can pass through a barrier that, according to classical physics, it has no business getting through. Imagine rolling a ball toward a hill. If the ball doesn't have enough energy to make it over the top, it rolls back. End of story. That's classical physics. But in quantum mechanics, the ball has a non-zero probability of appearing on the other side of the hill, even if it never had enough energy to climb over. It doesn't go over the barrier, it doesn't go around. It goes through, as if it briefly ceased to exist on one side and popped into existence on the other. It tunnels. Now, this isn't magic, even though it sounds like it. It's a direct consequence of the wave nature of matter. Remember de Broglie's insight. Particles are waves, and waves don't just stop dead at a barrier. If you have a sound wave hitting a wall, a tiny bit of the wave's energy leaks through to the other side. The thicker and denser the wall, the less gets through, but some always does. Quantum particles do the same thing. The wave function of an electron hitting an energy barrier doesn't drop to zero at the barrier. It decays exponentially inside the barrier, getting smaller and smaller. But if the barrier is thin enough, there's still some wave function left on the far side. And that residual wave function represents a real probability of finding the particle there. The particle has tunneled. The probability of tunneling depends sensitively on the width and height of the barrier. A wide, tall barrier? Almost no tunneling. A thin, shallow barrier? Significant tunneling probability. And this sensitivity is what makes tunneling so important in so many different contexts. Let's start with the biggest, the sun. Right now, at the core of the sun, hydrogen nuclei are fusing together to form helium, releasing the energy that lights up the solar system, warms the Earth, and ultimately sustains all life. But here's the problem. Those hydrogen nuclei are protons, positively charged particles, and like charges repel. To fuse, two protons have to get close enough for the strong nuclear force to grab them, and the strong force only operates at extremely short range. The protons have to overcome a huge wall of electromagnetic repulsion to get close enough. And here's the thing. The temperature at the center of the sun is about 15 million degrees Celsius. That's hot, but it's not hot enough. If you calculate the energy of a proton at 15 million degrees and compare it to the height of the electromagnetic barrier, the protons don't have enough energy to get over, not even close. Classically, fusion shouldn't happen. The sun shouldn't shine. But quantum tunneling saves the day. The protons don't need to go over the barrier. They tunnel through it. The probability of any individual proton tunneling through is vanishingly small, maybe 1 in 10 to the 28th power, for any given pair of colliding protons. But there are an incomprehensibly vast number of protons in the sun's core, and they're colliding constantly, billions upon billions of times per second. Even with that tiny probability per collision, the sheer volume of attempts means that tunneling happens often enough to keep the fusion fires burning. The sun has been doing this for about 4.5 billion years, and it'll keep going for another 5 billion or so, all thanks to quantum tunneling. Think about that for a moment. The light reaching your window on a sunny day was made possible by quantum mechanics. The warmth you feel, the seasons, photosynthesis, the entire food chain, all of it depends on protons tunneling through barriers they classically can't cross. The quantum world isn't some exotic abstraction. It's the reason there's a sun. Tunneling also explains radioactive alpha decay. Some atomic nuclei are unstable. They spontaneously eject an alpha particle, a cluster of 2 protons and 2 neutrons. Inside the nucleus, the alpha particle is bouncing around, held in by the strong nuclear force. But beyond the edge of the nucleus, there's an electromagnetic barrier. The alpha particle doesn't have enough energy to climb over it, but it can tunnel through, and occasionally it does. The probability of tunneling determines the half-life of the decay, how long, on average, you have to wait before a given nucleus decays. Uranium-238, with its thick barrier, has a half-life of about 4.5 billion years. Polonium-212, with a thinner one, has a half-life of about 3/10 of a second. Same physics, different barrier widths, vastly different timescales. And tunneling isn't just for nuclear physics. It's the working principle behind one of the most remarkable scientific instruments ever built, the Scanning Tunneling Microscope, or STM. Invented in 1981 by Gerd Binnig and Heinrich Rohrer at IBM's research laboratory in Zurich, work that earned them the Nobel Prize in 1986, the STM uses a phenomenally sharp metal tip, ideally terminating in a single atom, held incredibly close to a surface. A voltage is applied between the tip and the surface, and even though there's a gap of empty space, a tiny current flows. That current is electrons tunneling through the vacuum barrier between the tip and the surface. And because the tunneling probability depends exponentially on the barrier width, the gap distance, even a tiny change in the gap produces a large change in the current. Move the tip a fraction of an angstrom closer, and the current increases dramatically. This extreme sensitivity allows the STM to map out surfaces with atomic resolution. You can literally see individual atoms. Images from STMs look like landscapes of tiny bumps, each bump a single atom, arranged in the crystalline pattern of the surface. It's one of those technologies that feels like science fiction, but is science fact, and it works entirely because of quantum tunneling. Now, let's talk about where quantum mechanics really transformed the everyday world, because this is where the theory stops being a physicist's playground and becomes the infrastructure of modern civilization. And it starts with a question that might seem simple. Why do some materials conduct electricity and others don't? You've got a copper wire. Current flows through it. You've got a rubber band. It doesn't. Why? Classical physics could sort of hand-wave an answer, but quantum mechanics provides the real explanation, and it's beautiful. It involves a concept called band theory, and it's built on a principle we haven't talked about yet, the Pauli exclusion principle. Wolfgang Pauli, the sharp-tongued Austrian physicist who proposed the neutrino and dismissed bad papers as not even wrong, introduced this principle in 1925, and it might be the single most important idea in quantum mechanics that most people have never heard of. Here's what it says. No two electrons can be in exactly the same quantum state at the same time. They're not allowed to share. Two electrons can occupy the same energy level, but only if they have opposite spins, one spinning up, one spinning down. After that, the next electron has to go to a higher energy level. This one rule explains the entire periodic table. It explains why atoms have the chemical properties they do, why the noble gases are inert, why metals conduct, why the elements are arranged the way they are. Electrons fill up energy levels from the bottom, 2 per level, and the pattern of filling determines everything about the atom's behavior. It's remarkable, one principle, and it unlocks the architecture of all ordinary matter. Now, take that idea and apply it to a solid. A crystal of silicon, say, with billions of atoms packed together. In a single atom, the energy levels are sharp and discrete. But when atoms are packed tightly together, their energy levels start to overlap and interact, and those sharp levels smear out into broad bands of allowed energies. Between the bands, there are gaps, ranges of energy where no electron states exist. These band gaps turn out to be the key to everything. If the highest occupied band is only partly filled or overlaps with the next band, electrons can easily flow. That's a conductor: copper, gold, aluminum. If the gap between the filled band and the empty one is enormous, like in diamond, with a gap of about 5.5 electron volts, no electrons can jump across at normal temperatures. That's an insulator. But if the gap is small, about 1.1 electron volts in silicon, then thermal energy at room temperature is enough to kick a few electrons across. That's a semiconductor. Semiconductors are where the magic of modern technology lives. When you deliberately add tiny amounts of impurities to a semiconductor, a process called doping, you can create materials with an excess of mobile electrons, N-type, or with an excess of holes, missing electrons that act like positive charges, P-type. Put N-type next to P-type and you get a p-N junction, the most important structure in electronics. At that junction, electrons and holes diffuse across the boundary, create an internal electric field, and establish a region called the depletion zone. This junction is the heart of the diode, the transistor, the solar cell, the LED. It's the reason your phone exists. The transistor, the device that replaced vacuum tubes and made modern computing possible, was invented at Bell Labs in 1947 by William Shockley, John Bardeen, and Walter Brattain. The story has drama. Shockley's original design didn't work because of surface states, electrons trapped at the semiconductor surface that blocked his electric field. Bardeen figured out why. Bardeen and Brattain then built a crude but working point-contact transistor using germanium and gold foil, demonstrating amplification on December 23, 1947. Shockley, furious at being excluded from the breakthrough, went off alone and invented the superior junction transistor. All three shared the Nobel Prize in 1956. Bardeen left for academia and won a second Nobel for superconductivity. Shockley went to California, founded a company, managed it so badly that his best employees quit, and started Fairchild Semiconductor, which spawned Intel, which spawned Silicon Valley. One man's toxic management style accidentally created the geography of the modern tech industry. And what those transistors do is fundamentally quantum mechanical. The band structure, the doping, the tunneling, the behavior of electrons and holes at the junction, all of it is governed by quantum mechanics. When Gordon Moore noticed in 1965 that the number of transistors on a chip doubled roughly every 2 years, he was observing a trend that would continue for decades. Your phone's processor has something like 15 billion transistors, each one a tiny quantum mechanical switch, operating on principles that Bardeen and Brattain first demonstrated with a piece of germanium and a triangle of gold foil. And there's another quantum technology you use every single day, probably without thinking about it. Lasers. The word stands for light amplification by stimulated emission of radiation, and that phrase, stimulated emission, goes straight back to Einstein. In 1917, he showed that there are two ways an atom can emit light. Spontaneous emission, the electron drops down on its own and spits out a photon in a random direction. And stimulated emission, a passing photon, triggers the atom to release its photon immediately, and the new photon is an identical copy, same frequency, same direction, same phase. Now you have two. Those two trigger more emissions, and you get 4, 8, 16, a chain reaction of perfectly identical photons. Coherent light, a laser. The first laser was built in 1960 by Theodore Maiman at Hughes Research Laboratories in Malibu, using a ruby crystal. People famously called it a solution looking for a problem. That turned out to be wildly wrong. Today, lasers are everywhere. Fiber optic communications, barcode scanners, laser surgery, manufacturing, CD and Blu-ray players, LiDAR in self-driving cars, and the LIGO gravitational wave detectors, which use laser interferometry to detect distortions in space-time smaller than a 10,000th of a proton's diameter. Every one of these applications traces back to stimulated emission, a quantum process Einstein predicted on paper more than a century ago. And then there are atomic clocks. Every cesium-133 atom in the universe has a hyperfine electron transition that oscillates at exactly 9,192,631,770 cycles per second. Not approximately, exactly. Since 1967, that frequency is the definition of a second. Atomic clocks based on this transition are accurate to about 1 second in 300 million years. Optical lattice clocks, the latest generation, are accurate to 1 second in about 15 billion years, longer than the age of the universe. And GPS depends on these clocks. Each satellite broadcasts a timestamp. Your phone measures the arrival delay, and from multiple satellites, it triangulates your position. A timing error of 1 microsecond means a position error of 300 meters. Without quantum mechanical atomic clocks, GPS wouldn't work. And there's a beautiful detail here. GPS has to correct for both special and general relativity. The satellite's motion makes their clocks tick slightly slower, about 7 microseconds per day lost. But their altitude in Earth's weaker gravitational field makes their clocks tick slightly faster, about 45 microseconds per day gained. The net correction is about 38 microseconds per day fast. Without it, GPS positions would drift by about 10 kilometers per day. Quantum mechanics provides the clock. Relativity tells you how to adjust it. And the result is that you can find any address on the planet to within a few meters. Abstract physics, concrete technology, in your pocket, right pains. And while we're talking about quantum technologies that most people encounter without realizing it, here's one more that's worth knowing about. MRI. Magnetic resonance imaging. If you've ever had an MRI scan at a hospital, you've been inside one of the most sophisticated quantum mechanical devices ever built. Here's how it works, in essence. Your body is mostly water, and water contains hydrogen atoms. Each hydrogen nucleus, a single proton, has a quantum mechanical property called spin, which makes it behave like a tiny bar magnet. Normally, these little magnets point in random directions and cancel each other out. But when you slide into an MRI machine, you enter an extraordinarily powerful magnetic field, typically about 1.5 to 3 Tesla, roughly 30,000 times stronger than the Earth's magnetic field. That field causes the hydrogen spins to align, either parallel or anti-parallel to the field direction. The parallel alignment is slightly lower in energy, so there's a tiny surplus of protons pointing that way. Then the MRI machine sends in a pulse of radio frequency radiation at exactly the right frequency to flip some of those protons from the lower energy state to the higher one. This is a quantum transition. The protons are absorbing photons of precisely the right energy to jump between quantized spin states. When the pulse ends, the protons relax back to their lower energy state, emitting radio frequency signals as they do. Sensitive detectors pick up those signals, and because different tissues have different concentrations of hydrogen and different relaxation times, the signals vary from place to place in the body. A computer processes all these signals and constructs a detailed three-dimensional image of your internal anatomy. No radiation, no surgery, no invasive procedure of any kind, just quantum mechanics, the quantized energy levels of nuclear spins in a magnetic field, turned into medical imaging of extraordinary clarity. There's another quantum phenomenon that's less visible in daily life, but profoundly important: superconductivity. Certain materials, when cooled below a critical temperature, lose all electrical resistance, completely. Not low resistance, zero resistance. An electric current started in a superconducting loop will flow forever, without any energy source, without any dissipation. It sounds impossible, but it's been measured. The longest tests have run for years, with no detectable decay in current. Superconductivity is a purely quantum mechanical phenomenon. It was first observed in 1911 by Heike Kamerlingh-Onnes in the Netherlands, when he cooled mercury below about 4 Kelvin, 4 degrees above absolute zero, and its electrical resistance vanished. But it took nearly 50 years before anyone understood why. In 1957, John Bardeen, yes, the same Bardeen who co-invented the transistor, together with Leon Cooper and John Robert Schrieffer, published what's known as BCS theory, the quantum mechanical explanation of superconductivity. The key insight is that at very low temperatures, electrons in certain materials form pairs, Cooper pairs, that behave collectively as a single quantum entity. These pairs are bound together by a subtle interaction mediated by vibrations in the crystal lattice, and because they act as a unified quantum state, they can flow through the material without scattering, without losing energy, without resistance. It's quantum coherence on a macroscopic scale, trillions of electrons all marching in quantum lockstep. Bardeen won his second Nobel Prize for this, becoming the only person to win the Nobel Prize in physics twice. Superconductivity is what makes MRI machines possible. Those powerful magnets are superconducting electromagnets. It's what makes particle accelerators like the LHC work. The magnets that steer protons around the 27-kilometer ring are superconducting, and superconducting circuits are the basis for the most common type of quantum computer qubit. The phenomenon is everywhere in cutting-edge technology, and it's 100% quantum mechanical. Now, but perhaps the most exciting thing happening in quantum physics today, the frontier where the theory is being pushed in genuinely new directions, is quantum computing. And to understand why it matters, you need to understand one thing about classical computers. They are fundamentally, architecturally limited in what they can simulate efficiently. And the thing they struggle with most is, fittingly, quantum mechanics itself. Here's the problem. A classical computer stores information as bits, zeros and ones. Each bit is in one state or the other, never both. And that's fine for most things. But imagine you want to simulate a quantum system, say, a molecule with 50 interacting electrons. Each electron can be in a superposition of spin up and spin down, and the state of the whole system isn't just a list of individual spins. It's a single, complicated, entangled quantum state, where the behavior of every electron depends on the behavior of every other. The number of possible states grows exponentially with the number of particles. For 50 electrons, you'd need to keep track of something like 2 to the 50th power, about 1,000,000 billion, possible configurations simultaneously. No classical computer on Earth has enough memory for that, not even close. Richard Feynman recognized this problem back in 1981. At a conference at MIT, he pointed out that if nature is fundamentally quantum, then simulating nature on a classical computer is inherently wasteful. A quantum computer, though, one that operates on quantum principles, could simulate quantum systems naturally and efficiently. It was a brilliant insight, though at the time it was more aspiration than blueprint. The theoretical framework came from David Deutsch at Oxford in 1985, who described a universal quantum computer. But the idea truly caught fire in 1994, when Peter Shor, a mathematician at Bell Labs, discovered an algorithm that could factor large numbers exponentially faster on a quantum computer than any known method on a classical one. And factoring large numbers is exactly the hard mathematical problem that underlies RSA encryption, the system securing your bank transactions, your emails, your medical records. Shor's algorithm implied that a sufficiently powerful quantum computer could break most of the world's encryption. Governments took notice. Banks took notice. Intelligence agencies definitely took notice. So how does a quantum computer actually work? Instead of classical bits, it uses quantum bits, or qubits. A qubit can be in a superposition of 0 and 1 simultaneously, not randomly, but in a precisely controlled combination. 2 qubits can exist in a superposition of all 4 possible 2-bit states at once. 3 qubits, all 8 states. 50 qubits, over 1,000,000 billion states. And you can manipulate all those states simultaneously through quantum operations, performing a kind of massively parallel computation that no classical computer can match. When you finally measure the qubits, the superposition collapses, and you get a definite answer. But the art of quantum algorithms is in setting up the superposition and the operations so that the right answer is the most probable one. Entanglement plays a crucial role too. Qubits that are entangled are correlated in ways that classical bits can't be, and those correlations are what give quantum computers their power for certain types of problems. It's not that quantum computers are faster at everything. For most tasks, your regular laptop will always be better, but for certain problems with the right mathematical structure, factoring, simulating quantum systems, certain optimization problems, they offer speed-ups that are not just incremental, but exponential. Building actual quantum computers, though, is an engineering challenge of extraordinary difficulty. Quantum states are fragile. Any interaction with the environment, a stray photon, a thermal vibration, a tiny electromagnetic fluctuation, can cause a qubit to decohere, collapsing out of its superposition into a definite classical state. And once that happens, you've lost the quantum advantage. This is why most quantum computers today operate at temperatures near absolute zero, inside elaborate dilution refrigerators that cool the system to about 15 millikelvin. The engineering is as demanding as anything humans have ever attempted. Several very different physical approaches are being pursued. Superconducting qubits, used by Google and IBM, are tiny circuits made of superconducting aluminum, cooled to near absolute zero. Electrons tunnel through Josephson junctions, thin insulating barriers, and the resulting current can exist in a superposition of flowing in opposite directions. It's quantum tunneling again, doing useful work. Trapped ion systems, pursued by companies like IonQ and Quantinuum, use individual atoms suspended in electromagnetic fields and manipulated with laser beams. They have longer coherence times, sometimes seconds instead of microseconds, but are slower and harder to scale. Microsoft has been exploring topological qubits based on exotic quasiparticles whose properties are inherently protected from local disturbances. It's a beautiful theoretical idea that's proved extremely difficult to realize in practice. The biggest practical challenge right now is error correction. Qubits make mistakes. They decohere. Gates are imprecise. Measurements occasionally give wrong answers. In a classical computer, you fix this by copying bits and using majority voting. But in quantum computing, the no-cloning theorem says you can't copy an unknown quantum state. So quantum error correction works differently. It encodes one logical qubit across many physical qubits using entanglement, detecting and correcting errors without directly measuring the fragile quantum information. The catch is that you need a lot of physical qubits per logical qubit. Current estimates suggest maybe 1,000 to 10,000 physical qubits for each reliable logical qubit. So when people talk about needing a 1,000,000-qubit machine, they're really talking about maybe 1,000 logical qubits, each built from 1,000 or more noisy physical ones. In 2019, Google claimed quantum supremacy with their 53-qubit Sycamore processor, performing a specific calculation in 200 seconds that they estimated would take a classical supercomputer 10,000 years. IBM pushed back on the classical estimate, but the milestone was real. Since then, the field has continued to advance. The focus has shifted from qubit counts to error rates, because reducing errors is arguably more important than adding qubits. Google demonstrated in 2023 that their error-corrected logical qubits actually got better as they added more physical qubits, a crucial threshold proving that error correction was genuinely working, rather than adding more noise than it removed. What will quantum computers actually be useful for? Probably not replacing your laptop, but for simulating quantum chemistry, understanding how molecules interact, designing new drugs, creating better catalysts and batteries. They could be transformative. For breaking existing encryption, they're a serious threat, and the world is already transitioning to post-quantum cryptographic standards to prepare. For certain optimization problems in logistics, finance, and materials science, they may offer significant speedups. And perhaps most excitingly, the theoretical tools developed for quantum information science have already fed back into fundamental physics, offering new ways to think about black holes, the nature of space-time, and the deep connections between information and reality. And now we've come a long way. From Planck's reluctant quanta in 1900 to quantum computers in the 2020s, from a quiet German professor trying to explain why hot things glow, to machines that use the entanglement of atoms to perform calculations no classical device could ever match. And along the way, quantum physics has given us semiconductors, transistors, integrated circuits, lasers, LEDs, MRI machines, atomic clocks. GPS, electron microscopes, superconductors, nuclear energy, and our understanding of how stars shine and atoms bond and matter exists at all. Not bad for a theory that started as a mathematical trick nobody believed in. But I want to end tonight with something that doesn't get talked about enough when people discuss quantum physics, and it's this. We still don't really understand it. Not in the deepest sense. The mathematics is clear. The predictions are staggeringly accurate. Quantum electrodynamics predicts the magnetic properties of the electron to 1 part in 10 trillion. No theory in the history of science has been tested more thoroughly or confirmed more precisely. But what the mathematics means, what it's telling us about the actual nature of reality, remains genuinely, profoundly uncertain. The Copenhagen interpretation says, don't ask. The wave function is a tool for calculating probabilities, and asking what's really happening before a measurement is a question without meaning. Many physicists work comfortably within this framework and consider the question settled, but others disagree, and their alternatives are fascinating. The many worlds interpretation, proposed by Hugh Everett in 1957, says there's no wave function collapse at all. Every quantum measurement splits the universe into branches, one for each possible outcome, and all branches are equally real. When you measure an electron's spin and find it pointing up, there's another version of you, in another branch of reality, who found it pointing down. The universe is constantly branching, endlessly, into an inconceivably vast tree of parallel realities. It sounds wild, but the math is clean, and a growing number of physicists take it seriously. The pilot wave theory, developed by David Bohm in 1952, says particles really do have definite positions at all times. They're guided by a pilot wave that obeys the Schrödinger equation. It reproduces all the predictions of standard quantum mechanics while restoring a kind of determinism. The price is non-locality. The pilot wave connects distant particles instantaneously, which Einstein would not have liked. And there are others. Relational quantum mechanics, QBism, objective collapse theories. Smart, serious physicists disagree passionately about which, if any, is correct. And the remarkable thing is that all of these interpretations make the same experimental predictions for every experiment we've been able to perform so far. They disagree about what's real, but they agree about what you'll measure. Which means, at least for now, the question of what quantum mechanics actually tells us about the nature of reality remains open. And maybe that's the most honest thing you can say about quantum physics. It gives us answers that work, wrapped in mysteries that remain. The universe doesn't owe us an intuitive picture. It doesn't have to make sense in terms of things we can visualize or touch. It just has to be consistent, and it is. Wildly, beautifully, stubbornly consistent. So as you lie there, letting your breathing slow and your thoughts drift, here's something worth holding on to. Every atom in your body was forged in the core of a star, through quantum mechanical processes, nuclear fusion, powered by quantum tunneling. The carbon in your muscles, the calcium in your bones, the iron in your blood, all assembled by quantum mechanics in stellar furnaces billions of years ago, then scattered across space by supernova explosions, then gathered together by gravity into a new solar system, a new planet, and eventually, into you. You are made of star stuff, and that star stuff was made by quantum physics. The same strange rules we've been exploring tonight. Quantized energy, wave-particle duality, tunneling, superposition, entanglement. Those are the rules that built you. Every atom, every molecule, every heartbeat. Right now, quantum mechanics is at work in your body. Electrons are sitting in their probability clouds around atomic nuclei, obeying the Pauli exclusion principle. Chemical bonds are forming and breaking through quantum mechanical electron sharing. The photoreceptors in your eyes, if they're still open, are absorbing photons one at a time and converting them into neural signals through quantum transitions in molecules of retinal. Your cells are metabolizing food through enzyme-catalyzed reactions, where quantum tunneling of protons plays a measurable role. Some researchers have even found evidence that quantum effects play a part in how birds navigate the Earth's magnetic field, and in the remarkable efficiency of photosynthesis. The universe figured out quantum mechanics long before we did. Stars have been fusing hydrogen through quantum tunneling for billions of years. Atoms have been obeying the uncertainty principle since there have been atoms. The quantum world isn't something we invented or discovered in any ordinary sense. It's something that was always running, silently, underneath everything, and we're the part of the universe that finally noticed. And what we noticed is this: the deepest layer of reality is stranger, richer, and more subtle than anything our ancestors imagined. It's a world where particles are waves and waves are particles, where things don't have definite properties until you look at them, where two particles on opposite sides of the cosmos can be connected in ways that defy spatial separation, where the mere act of observation changes what you're observing. It's a world that resists easy stories and intuitive pictures, and that's okay, because the mathematics is there, steady as bedrock, giving us predictions we can rely on to build the technologies that shape our lives. Planck started it, reluctantly, with a formula that fit the data. Einstein pushed it further than Planck wanted. Bohr built an atom out of quantum rules. De Broglie made matter into waves. Heisenberg and Schrödinger built the theory. Born told us what the theory means. Dirac predicted antimatter from pure mathematics. Feynman, Schwinger, and Tomonaga tamed the infinities. Gell-Mann found quarks hiding inside protons. Bell proved the debate could be settled by experiment, and Aspect settled it. And now, in this century, engineers and physicists are harnessing entanglement and superposition to build quantum computers that might one day transform medicine, materials science, and our understanding of the cosmos itself. It's one story, one long story, stretching from a conference room in Berlin in 1900 to a laboratory in Delft in 2015, to a particle accelerator beneath the Swiss Alps in 2012, to a dilution refrigerator in a Google lab running at temperatures colder than deep space. One thread spun from Planck's constant, that tiny, tiny number, 6.626 times 10 to the negative 34, that keeps appearing everywhere, setting the scale for the quantum world, the boundary between the smooth classical universe we perceive and the grainy, probabilistic, deeply strange universe that actually is. That's a good thing to carry into sleep. The knowledge that the world beneath appearances is richer and more wonderful than it looks. That understanding, even a piece of it, is one of the great achievements of the human mind. That the same laws governing the insides of atoms also built the stars, and that the light of those stars, traveling for billions of years, is arriving at your window right now as individual photons, each one a quantum of energy, each one a tiny echo of the revolution that Max Planck started, reluctantly, on a December evening in Berlin, more than a century ago. Let that settle. Let the ideas drift, and let the quantum mechanics that runs quietly through every atom of your body do what it does, carrying you, gently and reliably, into sleep.